Okay, I guess we'll get started. So today I want to show you how to implement a generic collection. So we've implemented a list, a stack, and a queue a couple different ways, right? So with the list we used an array for storing the elements, and for the stack and queue we used nodes to store the elements. Right? Both types of implementations that we used, there's a pretty serious disadvantage. Right? And that is the collections that we implemented can only store ints. Right? If you want to, if you wanted a type safe, so one of the advantages is that the collections we implemented are also type safe. Right? So that they store ints and you can only put ints into the collection. Right? Unless you do something silly like cast a double to an int and then try to shove it into the collection. But they're type safe at least, which is good. Right? If you want a type-safe list of something else, right? So a type-safe list of strings, you now have to make an entire new collection, right? So basically what you end up doing is you take your list or your stack or your queue, right? Copy the header and C files, change every instance of int that every element instance of int to string or something else, right? To a char array, right? And then you've now got an implementation that can store strings, right? But that means there's a bunch of code copying that's happening, right? If you now want a list that can hold doubles, now you've got to do the same thing all over again, right? So this involves a lot of manual copying and code duplication on the programmer's part, which is no fun. It's also error prone. So you want to avoid doing that if you can. So there's a language called C++, which is it's an object-oriented. It's not quite an object-oriented version of C, although that's kind of the way it started out. It's grown into something much more. But you can sort of think of it as being C with objects. So C++ has a mechanism called templates. And the template mechanism does exactly this. Right? So you can create a generic collection, but every time you make a generic collection of a different type, the compiler synthesizes a new class, right, to store elements of that type. Right? But the compiler does all the work for you, which is nice. Right? So there's no manual code duplication. There's a lot of code duplication still happening, but at least the compiler is taking care of it for you. Right? I should also point out that templates are much more sophisticated than this. In fact, the template mechanism in C++ is actually a language of its own. Now, Java also has generics, right? So in Java, when you used a list, you always said you had a list of string or a list of integer or a list of double or something, right? So in Java, the compiler does not make a new class for every different type. So instead, what the compiler does is it checks your program, makes sure that every access to the collection is type safe. Right? So you're only putting strings into a list of strings. When you're taking something out, you're treating it as a string. Right? The compiler checks all of that and then throws away your type. Right? So at runtime in Java, a list of strings is actually a list of object. Right? So Java does what's called type erasure. It throws away the generic type and hides all of the casting that you have to do from the programmer. Right? That saves you from having to do any code duplication. Yeah, so that's good. So C++ and Java, they have mechanisms for creating generic types. C does not. Right? So the fundamental problem in C is that, well, not the fun. I mean, there's no type that can represent any object. Right? The closest thing that we have is void star. Right? So void star is a pointer that can point to any object. Right? So that means you can make a collection, right, where the elements in the collection are all void star pointers. Right? So now you're going to hold pointers to elements. Now the problem is void star can point to anything. So you lose all the type safety that we have. Right? Because now you can put anything into the collection because the elements are all void star pointers. Right? So this ends up resembling a Python collection. Right? So in a Python list or a dictionary or a set, right, you can shove whatever you want into an instance of a Python collection. Right? So Python also has no built-in type safety with its collections, right? Unless you use one of the extensions to the language. So what that means is now you lose type safety, you get genericity. Right? The programmer is now responsible for all the types, for the types of all the objects that they put in and take out of the collection. Right? So this is what we're going to end up doing in C as well. Right? So I want to change the element type from int to void star. Right? So changing the node structure to do this is trivial. Right? Instead of int elem, we now have void star elem. Right? So our elements are going to be pointers to values. Right? So that's easy. No big change there. OK, now I want to change. I want to work with the stack implementation. So now we have to go and look at what the stack implementation actually does to figure out what changes do I need to make. Right? So let's quickly do that. So here's stack.c. You can see I've already made the change to the node class, to the node struct, sorry. Right? The stack struct doesn't have to change, right? Because it's just a node and a size. Right? Now when we look at init, so init's the thing that makes an empty stack. Right? So the question you have to ask is, does init involve a node at all? Right? And you scan through the code and you say no. Right? There's no mention of a node, so we don't care about that. So init doesn't have to change. Right? Is empty and size? Well, again, there's no reference to a node of any kind. So also they don't have to change. But when you get to push, right, we're going to add an element to the stack. So that type there has to change. Right? It used to be int elem. It's now void star elem. Right? So when someone pushes an int onto the stack, right, they're now pushing a pointer to an int. Okay. Now happily, the code in stack in the push doesn't have to change. Right? Because the only reference to a lem is the assignment here. Right? And you can assign a pointer the same way you can assign an int value. So nothing changes there. Pop. So pop used to return an int. Now it has to return a pointer to void. Right? So it has to return a pointer to some element. And this is the problem when you use this, implementation. Right? When you pop something from the stack, you're getting back a void star point. You're getting back a pointer to void. Right? Or a void pointer, sorry. You're getting back a void pointer. So that means in order to do anything with the type, you now have to cast it to something else. Right? You have to cast it to the type that you think is actually in the collection. Nothing else changes, right? Because there's no reference to the node. Right? So that's, that's interesting. Free the old top node. So this is the node. There's a mistake here. There actually is a change that has to be made. So I'll get to that in a second. I just saw that. Cool. All right. So functions that don't change. Init is empty, size don't change. Right? Push and pop, push anyway has a small change. Right? You just change the parameter. Right? Pop, you change the return type, and I guess when I fix the slides, we'll have to make another change to this as well. Right? Printing a stack becomes a problem. Okay? So printing a stack actually becomes a big problem. So if you look at the code for printing a stack, right, you'll quickly realize that there's a serious problem. Right? So as the person implementing the stack, I have no idea how to print an element, right? Because the element type is void star. Right? So I have no idea how to print a pointer to void, a void pointer. Right? So the problem is I don't know what the element type is. Right? I have no idea what the actual type is. So there's no way I can print it. Right? Furthermore, the user of the stack is not required to use an int or a double or a float or something like that. Right? They can push structures or something else onto the stack. Right? They can push anything onto the stack. Right? And there's no good way to be able to, there's no way that as the implementer, I can possibly know how to print that thing. Right? And so if we go back to, oh no, I can't go back. No, that's fine. I'll just go back. Right? So before, in the previous implementation, we just print out an int. Right? I know how to do that. Right? That's printf%d. Right? That's easy. But if I was asked to print out some kind of structure, I have no idea how to print that. Right? I don't even know what's in the structure because all I have is a pointer to void. And the same thing happens when you try to free the stack, which is why I said there's a bug in the pop method, pop function. Right? So when you free a stack, we don't know if the user wants us to just free the memory associated with the stack structure itself, or do they want us to free all the elements that are also in the stack. Right? They might want us to do either one of the two. Right? So that's fine. If they do want us to free the elements that are in the stack, I have a problem because I don't know how to free the element in the stack. Right? So you saw, remember with the list, list struct that we implemented. Right? We had to create a special function that actually frees the structure and all of the elements and all the elements, right? With the stack and the queue, we also had to implement our own free function, right? That went in and freed all the nodes, right? There's no way I can know how to do that if I don't know what the element type is that's being stored in the structure, right? So now I've got these two big problems that I have to solve, right? So one option is to not solve the problem, right? So one option is to say, well, I'm not going to print the stack. If you want to print it, it's up to you, right? You figure out how to do it. So that's a possible solution, right? Another possible solution is, well, I'm not going to, I will never free the elements that you put into the stack, right? That's the user's job to do that, right? So those are both possible options. They're a little unsatisfactory, though, right? So there is a way to solve this problem, right? And so the way to solve the problem is to make the following observation, right? So if I want to print or free an element, right, it can be done. It's just you need an algorithm to do it, right? So to print some sort of structure, right, I need to know what the members of the structure are and how to print each member, right? But you can describe that in an algorithm, right? To free an element like a structure, I need to know what's in the structure and how to free each member. Right? But again, you can you can describe that as an algorithm, right? And in C, an algorithm is just a function or functions, right? But you put those two things together, and you can quickly realize that if you had a mechanism that lets pass a function to a function, then you can actually solve this problem, right? So that's what I want to talk about today. So how do you pass a function to a function in C? Well, you have pointers to functions, right? So I mentioned this briefly in one lecture, I think last week, right? So you can actually create a pointer to a function in C, right? So here's a function here, right? This is the generic form of a function, right? You've got some return type, it has some name, and then you've got a list of parameters, right? So the parameters include the types of, the parameter list includes the type of each parameter, right? We don't actually care about the names. We just care about the types. Right? So return type, function name, parameters, right? If you have a function of that form, then you can create a pointer to that function by writing this, right? So basically, you just copy everything from here, right? And then you change the function name to star something, right? So you take the function name, put it in brackets, and write star in front, right? To indicate that it's a pointer. Right? So that declaration there will actually make a pointer to a function having this form, right? And the pointer name will be whatever name you decide to give it here. All right, so one more time. You've got a function, right? Return, name, parameters. The pointer to that function is just the same return type. Then inside round brackets, star, some pointer name, and then the parameters. Right? So all you're doing is changing the function name. Right? That's all you're doing. Right? And that gives you a pointer. Okay, so let's take a look at some examples. Okay, so I've got 4 functions here, right? So I hope everybody can read these 4 functions without any difficulty at this point in time, right? So function number 1, right, returns void, right, has no parameters, right? It does nothing, so it literally does nothing, right? All it does is return. Okay, function number 2, right, returns void, has one parameter of type int, right? Function number 3 returns an int, has 2 int parameters, right? And function number 4, okay, so it returns a pointer. Returns a pointer to a double, right? So it returns a pointer to a double, and has 1 double input, right? So there are my 4 functions. There's a 5th one here, but it's a little bit more complicated, right? So I'm going to ignore the 5th one for now, right? So how do I make a pointer to void something void, right? So the way to make a pointer to that is just do, right, return type, same list of parameters, right? Round brackets, throw in a star and give it a name, right? So that says that ptr1 is a pointer to a function that returns void and has and accepts no arguments. Right? So that's a pointer, and I'm going to make it point to the do nothing function. Right? So how do I make it point to the do nothing function? I need the address of the function. Right? Sounds weird, but C functions have addresses, right? So you can take the address using the ampersand operator, right? And then the name of the function. Right? So that declares a pointer called ptr1. Right? The declaration is very strange, right? Because you're used to writing variable name or variable type, then name, then something. Right? When you're declaring a pointer to a function, it's a little strange. Okay, so what about the print int function? So print int, let's take a quick look at it again. Right? Returns void, has one int parameter. Right? So to take a pointer to that function, right, you write void. Right? You write the parameter list, so that's int. Right? Round brackets in front of the parameter list, star some name. Right? So ptr2 is a pointer to a function that returns void and has one int parameter. Right? And so I'm going to take the address of print int, and that'll initialize my second pointer. Right? Now you can make this pointer point to any function that has the right form. Right? So if I put in another function up here, right? So it returns void, some function, int j. We'll do nothing here. Right? So these two functions, right, they have the same return type, right, same parameter list. So I can make that second pointer also equal some func. Right? So that works fine too. Right? So ptr2 is just a pointer. It has a weird declaration, right? But otherwise it's just a pointer. Okay, what about the next one? So max, right, returns an int, has two int parameters. Has two int parameters. Right? So if I want to take a pointer to that function, you write int, right? You write int. You copy over the parameter list, right? You don't need the names of the parameters. In round brackets, star, and then some pointer name. Right? So ptr3 is a pointer to some function that returns an int and has two int parameters. Right? And I can make that point to the max function like that. Right? Again, if you had another function that had the same return type and parameter list, you can make it point to that function instead. Okay, this one's a good one. Okay, so here's a function that returns a pointer to a double. Right? So if I want to take a pointer to this function, well, it's the exact same thing. Right? Copy over the return type. Right? So there's my return type. Right? Copy over the parameter list. Right? Inside round brackets after the return type, right? Star some pointer name. Right? So this says ptr4 is a pointer to a function that returns a pointer to a double and has one double parameter. Right? Okay, now the last one. So here's a function called makeInt. Right? So all this does is it computes the maximum of a and b and then returns a pointer to the value. Right? So it allocates space on the heap for an int value. Right? Does something very strange here and then returns I. Right? So it returns the value. Right? So I'll explain the something strange in a moment. Right? Let's look at that third parameter right there. Right? So when you look at that thing, you say, oh, well, that's a pointer to a function. Right? That's what it looks like anyway. Right? It's a pointer to a function. Right? So fp is a pointer to a function whose input is int. Whose return type is int. And it has two int parameters. Right? So it has two int parameters. So that's a pointer to a function. Right? Now here, I'm going to call that function. Right? So fp is a pointer. Right? So to dereference the pointer, you write star fp. Right? So when you dereference a function pointer, you get the function. Right? So I'm now able to call the function. How do I call the function? Well, I have to pass in two ints because this is a function. This is a pointer to a function that has two int parameters. Right? So I need to call it. with two int values. So here I'm going to choose a and b. Right? So all I'm doing is calling another function from inside this function. Right? How do I call the function? Well, I call it via a pointer to that function. Right? Now, what pointer am I going to pass? I'm going to pass the pointer to max. Right? So down. No, I'm actually I don't call it at all here, do I? Do I make int? How did I call this? Oh yeah. Okay, so all right. Okay, so to call my make int function, I'm going to call it down here. Right? Oh, I called it in a very bizarre way. But anyway, okay, so anyway, here's my, right? Okay, so let me back up here. All right, so I want to make a pointer to this function now. All right? So how do you make a pointer to the function? Well, you take the return type, right? You take all of the types sitting in the parameter list, and you just copy those over. Right? So there's my return type, right? It's a pointer to int. There's my parameters. Right? Notice you can put in the variable names if you want to. It doesn't matter if they match or not, right? So if you don't want, you don't have to put them in here if you don't want to, right? So you can delete the A and you can delete the B, right? You can even delete the FP. So you could write it like that if you wanted to. I think it looks a little easier to read if you leave the pointer in, but anyway. Right? So, oh, and then inside round brackets, right? Star some pointer name, right? So pointer 5. Oh, it even tells you, hey, that's cool. Pointer 5 is a pointer to the make int function. That's pretty cool. I didn't know code did that. Right, but that's exactly what it's saying, right? Pointer 5 is a pointer to the function make int, right? Now, I can call make int if I want to, right? So I can call the function via the pointer, right? So how do I call the function via the pointer? Dereference the pointer. That gives you the function, right? I need two ints. So there's A, right? And there's B, right? I'm going to pass in 5 and 10. And now I need the pointer to a function that takes in two ints, right? So that's pointer 3, which points to the max function, right? So all this does, when I call the function, right, is it calls max here, right? And so I becomes the max of A and B, which is 10 in this case. Right? Do I actually print it out? Yeah, I print it out. So if I've done everything right, oh, I don't know if I built it. I did not, so GCC. Pointer. Now watch, this is not going to work. Oh, it worked, okay. Pointer. Okay, so there you go, yeah, x equals 10, right? Which is what you expect, right? Because x is, oops, sorry, x is the max of 5 and 10 is 10. Right, now that last one at this point in time, right, since this is the first time you've seen a pointer to a function, that last one's hard to read, right? So I don't expect you to understand how to read that right now, but you need to digest that and understand what's going on there. Okay, the other ones though, I think you can understand, right? Right, so taking pointers to these functions ought to be doable. All right, but that last one I admit is that's a little confusing to read. Right? Okay, anybody have any questions, or should I go over that one more time? Anybody? Super. So I got a pointer to a function, right? So I've got pointers to functions, and I can call those functions given the pointer, right? To call the function, you dereference the pointer. Right? That gives you the function, and then you just pass in the parameters. Right? All right. So how do I print an element? Right? Well, I want to encapsulate the printing of an element inside a function. Right? So my elements have type void star. Right? So I have void pointers to the elements in the collection. Right? So to print an element, I want to call some function that can take in an element and print it. Right? I'm going to make it const because I don't want to change the element. Right? Printing an element shouldn't change it, so I'm going to mark it const. Right? To free, therefore to print. Oh, right. Okay. So I want to call a function that looks like that to print each element. Right? to call that function from inside the stack implementation, I need a pointer. Right? So that means I want a pointer of the form void, right? Const void star, right? And then some kind of pointer here. Right? So that's what I want. Now, I don't want people to write that, right? Because it's no fun writing this, right? So as the implementer of the stack struct, I'm going to provide a type def for this pointer, right? And that'll save anybody from having to figure this out, right? So I'm going to make a type def, right? Now to make the type def, again, it's a little weird, right? So normally it's type def, the thing you want to have, the thing you want to replace, and then the name of the type, the alias, right? The name of the alias. With pointers to functions, it's a little bit different, right? So with a pointer to a function, you write the pointer to the function, right? So void, that's the return type, right? The inputs are const void star, right? And then in here, you write star and then the name of the alias, right? So in other words, I want to create the name, the typed def name, print elem func, that people can use instead of having to write that. Right? So print elem func is just the short form, or is just an alias for a pointer to a function that can print an element. Right? That's all it says. So print elem func is just an alias for a pointer to a function, taking a void star pointer and returning void. Right? All right. Now freeing an element is almost the exact same thing. Right? So to free an element, right, I have to pass in I want to call the function that can accept a pointer to the element, right? And then that function will do all of it, everything it needs to do to free the memory associated with the element. Right? Now to call that function, right, I need a pointer to that function. So I want a pointer of the form void, right? Void star, and then the pointer type here, the pointer name there, right? So again, I don't want people to have to write that every time, so I'm going to make a type def, right? So type def void, so that's the return type of the function, right? That's the parameter types of the function, right? That's the name of the alias that you can use, right? So free elem func is an alias for a pointer to a function, right? It's an alias for a pointer to a function that can free an element, right? And print elem func, it's just an alias for a pointer to a function that can print an element. All right, so what does this actually look like when you code this up? So stack.h. So in the header file, right? So the header file is the file that people will include when they go to use your stack, right? So I'm going to add my two type defs. Right? So there's type def for print elem func, right? So that's a pointer to a function, right? That can print an element, right? There's my type def for a pointer to a function that frees an element. Right? Anybody who's using my stack implementation can just write that for the type. Right? So when they want a pointer to a function that can print an element, they can just write print elem func, right? And then assign it a value. Right? So that's your type. Right? Free elem func, that's your type for a pointer to a function that can free an element. Right? Now, free and print have to change. Right? So free and print, to free a stack, right, I'm going to allow the caller to pass in a function, to pass in a pointer to a function that can free an element, right? If they pass this in, so here we go, free the memory associated with a stack, right? If free elem is not null, right? Free elem func is not, if free elem is not null, right? So that function, if that pointer is not null, right, then stack free will go in and free every element that's in the stack as well. Right? It'll free all the memory associated with each element. Right? If it is null, then it won't free every element that's in the stack. Right? It'll let the caller deal with freeing the elements themselves. Right? Okay, now what about printing? Right? So to print a stack, right, I need to know how to print each element. So we're going to ask the user for a pointer to a function that can print an element. Right? Now, I need that function because there's no way for me to print an element if I don't have it, right? Because I don't know what the element type is. right? And so we get undefined behavior if print elem is null, right? So anything can happen if they pass in a null pointer for the printing function. Okay, now what does the source code look like? Okay, to free, so freeing a stack, it looks the same as before, right? You're going to free every node that's in the stack, right? So that all stays the same, right? So starting at the top node, right? I'm going to move along the nodes and free each node, right? I'm just going to march along the nodes, following the next pointer each time, right? Freeing the nodes as I visit them, right? Now, if the pointer to this function is not null, I'm also going to free the element, right? So if that pointer is not null, right, free the element. How do you free the element? Well, you call their function, right? How do you call the function? Well, that's a pointer to a function, so you just dereference the pointer, right? So star free elem, and then you pass in the element that you want to free, right? So that's just n arrow elem, right? And so that's the magic that lets this all work, right? The fact that the caller or the user can pass in the function that you need to use is what makes this all work, right? Okay, now what about printing? So this is the recursive version of print, so the interesting stuff happens down here, right? Now here, I just used to have a printf where I printed out the element, where I just printed out the integer, right? So now instead of printing out the integer, I need to print the element. Well, how do I print the element? Well, I've got a pointer to a function that can print an element, right? So dereference the pointer, pass in the element to print, right? And now the user's function will print the element, right? And then I'll print the separator after it, right? And away you go, right? So again, the fact that we're asking the user to pass in some required functionality is what makes all of this work. The demos. Okay. Stack demo one. Anybody have any questions so far? All right. So does this actually work? Okay, so I'm going to make a stack of strings, right? So to print out the stack, I need to provide a function that can print out a string, right? So I have to define, as the user of the stack now, this is my responsibility, right? That function has to have a certain form, right? It has to have the form that's defined in the header file, right? So in other words, it has to return void. It has to accept a const void star, a const void pointer, right? Okay, so my printing function returns void, and it has a parameter whose type is const void star, right? So I can take a pointer to this function and pass that to the stack now, right? How do you print this string? Well, the problem is it's a void star pointer, right? So I have to cast it back to its actual type, right? Now I'm the one that's providing this function, right? I'm the user of the class. I'm the user of the stack. I know that my stack is a stack of strings, right? So I know that I know that S is actually a car array, right? So in my function, I'm going to cast S to a car array, right? Or to a pointer to car, right? And then I can print that using %s, right? So print a string, right? And that's all you have to do. Okay, so how does this work? Well, everything's the same as before, right? I make a stack, right? Nothing changes there. I can ask, is the stack empty? Nothing changes there. Now, when I print the stack, this is where something changes, right? So when I print a stack, I have to give it a pointer to a function that can print an element, right? In this case, it's a stack of string, so I need to give it a pointer to a function that can print a string, right? Well, that's just my print string function, right? So I just take the address of print string and pass that to the function, right? Now, when the stack goes to print the elements in the stack, right, it will call this function for each element. Right. And same down here, right? So when I, oh, sorry. Okay, so here are the strings that I want to push onto the stack, right? It's a two-dimensional array. Why is it a two-dimensional array? Because each one of these things, right, each one of these strings is actually an array itself, right? Because that's how C's implement strings, right? So I have 5, right? I have an array of size 5, 1, 2, 3, 4, 5, right? Each element in the array is 10 characters long, right? Or there's storage for 10 characters, right? So ONE fits inside 10, TOW fits inside 10, and so on and so forth, right? So each one of these, so strings square bracket I, that's a pointer to a car. That's a car array, right? It's a string, right? So I can push each string onto the stack, right? And then I can print the stack as I push each string on, right? Does this work? Well, let's see. Right? In fact, it does work, right? So the empty stack, right? There's nothing. Stack of size 1, so I push the 1, the ONE, onto the stack, and there it is, right? Then I push TWO, right? And there it is. Then I push THREE, and then 4, and then 5, right? And everything works just fine. Freeing the stack. Okay, now when I free the stack, right, I'm not passing in a function to free the storage for all of the strings, right? And why am I not doing that? Because that thing there, right, that array has automatic storage, right? In other words, I did not allocate space for the individual strings using malloc, right, or realloc or calloc, right? These are all defined. So the lifetime of all these strings is the lifetime of main, right? In other words, they don't need to be freed. They'll be freed automatically, right? Because these are all local variables, right? So those will be freed automatically. So they have automatic storage lifetime, right? So I don't have to free the individual strings myself, right? Or I don't have to ask the stack to free them. If you alloced space for all of these, right? So if you malloc space for these, then you have to ask, either you have to free them yourself or you have to ask the stack to free them. In this case, it doesn't matter because they're just in the main method. So when the main method stops, the memory is freed back anyway. Stack demo, oh wait, yeah, that runs. Okay, stack demo 2. Okay, now I want to make a stack of lists, right? Where we're using the list struct that we made a few days ago, right? So how do I print a list, right? If I want to print the stack, I need to tell the stack how to print each list element. Or sorry, how to print each element that's a list, right? So how do you print a list, right? Well, we were kind of lucky because we had list to string inside of our list struct, right? We actually made that function earlier. So this is easy, right? I don't have to regenerate a function to print a list, right? I just call list to string and then print the string, right? And then don't forget to free the string, right? Because list to string allocates memory for the string, right? If you don't free the string here, you're going to lose you will never return that memory back to the memory manager. How do you free a list? Well, fortunately, our list struct had a function to do that, right? So it was called list free, right? Now you might wonder, why can't I just pass a pointer to list free instead, right? Because list free does everything I need it to do. Right? The reason I can't pass a pointer to list free is because the parameter type is a pointer to a list, right? And the stack wants a pointer, wants a void star pointer, right? So you can't pass in the function list free directly here, right? So I need a little wrapper function that all it does is it accepts the parameter as a void pointer, but then casts it to a list pointer, right? And then calls list free, right? Okay, so how does this work? Well, I'm going to make a list, right? So here I have an array of lists, right? I'm going to initialize an empty list, right? Each time I initialize a list, I'm going to add some elements to it, right? And that will make my 5 lists. So I'm going to make the lists 0, and then 0, 1, and then there's a 0, 1, 2, and a 0, 1, 3, and a 0, 1, 2, 3, 4. Right? And then I'm just going to push a list onto a stack. Right? So I'm going to push 5 lists onto the stack. When I print a stack, when I print the stack, I pass in a pointer to the function that can print a list. Right? And when I free the stack, I pass in a pointer to a function that can free a list. Right? All right, this one works too. Right? So I'm going to push 5 lists onto this stack. Right? So the first list is empty. Right? The second list has only 1 element in it. The third list has 2. Right? The fourth list has 3 elements, and finally the last list has 4 elements. Right? And they're all pushed onto the stack. Right? You can see that they're all there. Right? So there's the element list of size 4, right? The list of size 3, the list of size 2, the list of size 1, and the list of size 0. Right? So they all actually get pushed onto the stack, and they all get freed correctly as well. Oh, sorry. All right. So there are some disadvantages to this implementation. Right? So disadvantage number 1, you have to be very careful when you use this stack implementation. Right? Because all the elements are pointers, are void pointers. Right? So they're pointers to something. Right? And that means the elements, right, they have to have a longer lifetime than the stack. Right? If the elements don't have a longer lifetime than the stack is going to have pointers to elements that don't exist. Right? So the elements should have allocated storage duration. Right? In other words, the elements, when you push an element onto the stack, either you're pushing on elements whose memory has been allocated using malloc, right? Or you have to make sure that the elements have a longer lifetime, or their lifetime, the lifetime of the stack is completely contained by the lifetime of the elements. Right? Otherwise, the stack ends up with pointers to elements that no longer exist. Right? So you have to be very careful when you use this thing. That's why if you go back and look at that source code, there's a bunch of comments in there that say caution. Especially here. Here. Right? So when I push these strings onto the stack, it's fine. Right? As long as it's fine because this is all in the main method, right? So when the main method stops running, the program's over. So the lifetime of these strings is it's a little bit longer than it's the same, or at least it completely overlaps the lifetime of the stack, right? So that's fine. So the stack never has pointers to strings that don't exist, right? In a second, I'm going to show you another example where you might run into a problem. Problem number 2, there's no static type safety. Right? So all the elements are just just void pointers. Right? Which means whoever's using the stack can push whatever they want onto the stack. Right? So they can push an int, then they can push a double, then they can push a string, then they can push a list, and so on and so on and so on. Right? Anybody who writes a function that takes in a stack, right, they now have a huge problem because they don't know what elements are in the stack. Right? It's fine if it's your own little program and you're using the stack struct yourself. Right? So I make a stack and I make sure I only push ints onto the stack. Right? Then you can write a function that takes in a stack and assumes that the type is int. Right? But no one can easily write a generic function that takes in a stack and does something with it. Right? Because you don't know what element types are in the stack. Okay, so no type safety. Here we go. Ignore print for now. So here I'm going to make a stack, right? And I'm going to push 3 elements onto the stack. So I'm going to push a string, then I'm going to push an int, and then I'm going to push a double onto this stack, right? Notice again, you've got this caution here, right? All of these values have automatic storage, right? So in other words, their lifetime is the lifetime of main. Right? If the stack has a longer lifetime than the lifetime of main, it'll have pointers to elements that no longer exist. Right? Okay, so how do I push these values on? Well, that's already a pointer, right? So I can just push that on, right? You don't need the cast to void pointer here, right? The void pointer will accept any pointer type, right? So I can push the string on. I can push the int on by taking its address, right? And I can push the double on by taking its address, right? You shouldn't do this, right? You really you have to be very careful when you do this, right? You really should allocate I using malloc, right? And you really should allocate D using malloc as well, right? To ensure that it has allocated storage. And then I'm going to print them. Now, how on earth do you print this if they all have different types, right? And the answer is it's not easy, right? And in fact, there's a comment here that says don't do this, right? So how am I going to do this? Well, I'm going to try to guess what this thing is, right? And this only works because I wrote the main method myself, right? So I'm going to try to guess what each element is. So I'm going to cast that pointer to a car star pointer, right? So I'm going to try to treat everything as a string, right? I'm going to look at the first character. If it's an H, right? Because I pushed hello onto the stack, right? So if it's an H, I'm going to assume that it's a string, right? So I'm going to print the string. If I dereference the pointer and take its int value, and if it's 1, right, I'm going to assume it's the 1, right? And then otherwise, I'm going to assume it's the 2, which is a double, right? This won't work in general, right? This only works because I happen to know what I pushed onto the stack, right? But does this work? It surprisingly does work. Right? So that does actually work, right? When you print out the stack, it does in fact print 2, 1, and then hello. Now here's the problem when you use this implementation, right? When you start popping stuff off the stack, right? So when I pop the element, right? What are you getting back? You're getting back a void. You're getting back a void pointer, right? So you have to cast whatever you get back to the type that you think the element is in the stack, right? This only works because I know what I pushed onto the stack. So I happen to know the first thing off is a double, so I can cast that to a pointer to double, right? The second thing I know happens to be an int, so I can cast that to a pointer to int. Right? And the third thing I happen to know was the string, so I can so I can cast that to a pointer to car. Right? But this is the problem you have when you work with this type of data structure. Every time you try to get something out of the data structure, you have to cast it to the type that you expect is there. Right? If you're careful, the cast will succeed. Right? If you're not so careful, you might end up casting it to something where the element type is wrong. Right? And then bad things happen. All right. Any questions? Oh, sorry. Anybody? All right. That's it for today.